All right. So, sorry. Yes. Okay, so the other type of graph, okay, that we are going to be looking at are velocity versus time graphs. And a velocity versus time graph and a position versus time graph can show exactly the same data, but they're going to look different. Okay? In showing the same data, they will look different. Right? Prime example is these two graphs here. They are showing the same data. Okay? This on the left is the position versus time graph. Right? And according to this position versus time graph, the object is traveling at a constant velocity because its position is changing by the same amount every second. Well, this graph is showing exactly the same thing. It's showing that the velocity is not changing. Okay? It's showing an object traveling at a constant velocity of 260 meters per second or so. Okay? Somewhere in there. Right? They don't look much alike, okay? But they are showing exactly the same thing. Now, if I wanted to calculate the average velocity of the object on this graph, could I do this? Y minus b over x. Okay? Because on this graph, b is, nope, hundreds at the bottom of this graph, right? That's the tricky part of this graph. Okay, it doesn't start at 0, right? So b is going to be 100 because that's where the line touches the y-axis, and I'm just going to use this point up here to get y and make it 1400. Okay, so I'm going to go 1400 minus 100, so there's y minus b, and x would be 5 seconds. Okay, so we've got 1300 divided by 5, which should be 260 meters per second. All right, so I calculated the average velocity of that object. Is that about where I said this line was on the velocity versus time graph? Okay, so they are definitely showing the same thing. Okay, on the position versus time graph, I calculated the displacement as part of my velocity calculation. I went final position, 1400, minus initial position, 100, and I got that the total displacement was 1300 meters. Okay. Could I calculate that from the velocity versus time graph as well? Okay. Really, this calculation here was just this, wasn't it? Okay. Can I do that same calculation on this graph? Right? I know the velocity, it's 260 meters per second. I know the time is 5 seconds. Can I use v equals d over t for that? Yeah. Okay. 260 times 5 should be 1300. Okay. Did I essentially then just calculate the area of this rectangle? Okay. So for those of you who are memorizing stuff from Science 10, one of the things you probably memorized was the area under the line on a velocity time graph is displacement. Okay. I just walked you through how to get that without memorizing it. It's just reasoning. Okay. All right, so those two graphs show exactly the same thing. What's the acceleration of this object? Zero. It's not accelerating, right? Both graphs are showing an object whose speed is not changing. Okay. The speed is constant, so the acceleration is 0. Okay, let's try something different. Okay, what's that object doing? Okay, started at a velocity of 100 meters per second and went to a velocity of 550 meters per second. Any change in velocity is called an acceleration. Okay, that's an object that is accelerating. Okay, it's showing the velocity changing over time. Everybody with me there? All right. In Science 10, you used this formula calculate acceleration. Okay? Change in velocity over time, VF minus VI over T. Your teacher may have written it like this. Sometimes it looks like that too. Okay? Delta just means final minus initial. Okay? So if I know the final velocity, and I know the initial velocity, and I know the time, could I calculate the acceleration from this graph? Okay. When I calculate acceleration, what am I really calculating about this line? Does this formula look like this? Right? That's where that formula comes from. V equals d over t and a equals v over t are both variations on the slope formula from different graphs. Okay? Since this graph is showing velocity on the y-axis, y minus b is final velocity minus initial velocity. X is time. Okay? Time's on the x-axis. Okay? That's where that formula comes from. So even though you didn't know it when you were using that formula in Science 10, you were really calculating the slope of a line on a velocity versus time graph every time you used it. Okay. All right. So let's calculate the velocity of this object then. We're going to go 550 minus 100. So we'll have 450 on the top divided by 5 seconds. Okay, that's a pretty big acceleration. 10 Gs, or almost 10 Gs. Like, you'd probably black out if you endured that for very long, like more than a couple of seconds. It would be very uncomfortable. If you've ever seen the guys who do like the G-force things, okay, where they spin them around really fast and then they black out, that's what that would be like. Okay. All right, questions on that so far, on the velocity versus time? All right, just a minute ago, I asked you to calculate the displacement of the object with the flat line. Can you calculate the displacement of the object with the slanted line? Okay, it's still just area under the line if we're memorizing from Science 10. Okay, but let's look at why it's that. That's supposed to be at the 5. That's not very straight. Try that again. Okay, so I have a triangle there. The triangle says that my velocity is changing. Okay, when I calculated the area of this rectangle, that was v equals d over t. Okay, everyone all right with that? Well, v equals d over t works fine as long as v is constant. Okay, v is not constant with my angled line. But here's what I can recognize. Okay, I still have an average velocity. Okay, somewhere along this line is my average. Where about would it be? Okay. Down here I'm going really slow. Down here I'm going really fast, or up here I'm going really fast. My average would be right in the middle, halfway between. All right, how do you calculate the area of a triangle? Base times height divided by 2. Now you guys just told me that the average velocity would be right in the middle, like half the height of that triangle. Base times height over 2. Okay, that's why it works. Okay, it finds the average velocity. Okay, if I calculate the area of a triangle and go base times height over 2, this height over 2 is calculating my average velocity and then multiplying it by time. Okay, because what's on the base of this the base of this graph? The base of this graph is time. Okay, all I'm doing is going d equals average velocity times time. Okay, just v equals d over t. Okay, ringing a bell. That might be new. Not everybody teaches it that way. Okay. All right, this is a velocity versus time graph. In this first part of the graph, what's the person doing? they're accelerating. They're going faster and faster. Okay, here they're traveling at a constant speed, and now they're not just slowing down, they're actually coming to a stop, right? Their velocity actually goes back down to zero. This is a graph of someone running in a race. Okay, first part of the race, you accelerate, then you run as fast as you can. You can't accelerate anymore because you hit your top speed, and then you hit the finish line and stop. You don't stop instantaneously because that would be like a line that's straight down. That generally ends badly for people. Okay, you would slow down gradually, okay, like that line. Okay, so off of velocity versus time graph, we can read the velocity of the object at different times. Okay, that's what it shows us. We know we can calculate acceleration if we find the slope, or we use A equals VF minus VI over T. And we can find the displacement of the object using average velocity times time, the area under the line. Okay, that's where we get that from. All right, so hopefully that's all review and hopefully all familiar to everybody. Okay, now I want you guys to try a velocity versus time graph question. So try number 6. This is the graph for number 6. Okay, let's have a look at this one because I didn't exactly go over how to do this. I thought I'd see how many of you would figure it out. If I want to calculate average velocity, I need total displacement and total time. All right. Can I find the displacement of the object during the first 20 seconds from this velocity versus time graph? Right? I just have to find the area of this triangle, right? Because that will be average velocity times time. So I'm going to take my 40 high multiplied by 20 over 2. So 20 times 20, that should be 400, right? Okay, so in the first section of that graph, the object goes 400 meters, and that takes 20 seconds. Okay, so the average velocity is 20 meters per second. Could I have also just gone, oh, well, it's accelerating, so the average velocity is 20? I could have also done that, right? Is the next part even easier? Okay, because the speed or the velocity of the object in the next part of the graph doesn't what? Doesn't change. So the average velocity is 40. Okay, and then for this part here, okay, well, it's going to go from 40 to 80, so the average will be 60 during that section. Okay, fairly straightforward. It's a lot less work than probably we envisioned initially. All right, still want you to do this part, the overall velocity, the average velocity over the whole trip. That is going to require you to get the total displacement over the whole trip and the total time, which you can read from the graph. So I'll give you a few minutes on that one before I go over that one. Okay, so let's have a look at this one. So we've already done the first part here. We said that the area of this first triangle was 400 meters. Okay, if I'm going to find the total, the average velocity, I need the total displacement, which is the complete area underneath this graph. Right, so the next shape I want to use is this rectangle here, and notice that it does go all the way over. I have to find the area under the line. That includes this little piece right here, okay, that's underneath there. So this rectangle here is 40 on the base, and it's 40 high, right? So 40 times 40 should be, what, 1,600? Sounds about right, okay? And then I've got this small triangle here on the top that is 40 high by 10 wide. So 40 times 10 is 400 divided by 2. This is 200. Okay, so we're going to have 2,200 meters as our total displacement. Okay, and our total time was 60 seconds. Okay. Okay, because it's 37. Right. Okay, questions on that one? Okay, I would totally expect that you would get a question like that maybe on a quiz tomorrow. since tomorrow's Tuesday. All right, I want you guys to try number 7 there. Okay, just you can draw the graph just roughly. Okay, but it says the person drives a car at 25 meters per second for 10 minutes. Car runs out of gas, so the driver carrying an empty gasoline can walks at 1.5 meters per second for 10 minutes to the nearest gas station. After 5 minutes to fill the can, the driver walks back to the car at 1.2 meters per second, and then the car is driven home at 25 meters per second. All right, so I want you guys to draw that graph. It doesn't have to be to scale, just give me kind of the general shape of it. All right, let's have a look at what this velocity versus time graph would look like. Okay, so I've got, kilometers per hour here. No, yeah, meters per second. Sorry, meters per second on the y-axis, and I've got minutes on the x-axis. All right, so first it says it travels at 25 meters per second, and it does that for 10 minutes. Is that what it was? Okay, so goes for 10 minutes. Then it runs out of gas, so the person walks at 1.5 meters per second for another, does it say 10 minutes? Yeah. And then they fill up the gas can, and that takes 5 minutes, so something like that. Right? So now we've got the gas can all filled up. Now we got to walk back to the car. Where does my graph have to go now? Because these were all positive, right? This was like, this is positive up here. This is 25. This is like 1.5. Where does my graph have to go? Down into the negatives. Okay. Does it keep going forward? Yes, because sometimes, guys, when I give this question, people don't do this, which is what they should do. They go along here, and then they go down to negative 25, and then they go all the way back home. Sometimes they do this. What are you doing when you do that? Going back in time. Okay, you got to make sure you understand what you're doing when you draw on a graph. Okay, if you go this way to the left along a time axis, you are going back in time. You are arriving back when you arrived, not only where you took off from, but when you took off from that place, and that's not possible. Okay, because you're getting back there at time 0. So unless you know something about the space-time continuum that I don't, okay, the last time I checked, you can't do that. It does. It says a person drives a car at positive 25 meters per second. So positive 25. No, it says at negative 25. You can't see it here because I cut it off, but it does say negative 25 there. All right, so we would draw it, okay, something like that, walking back to the car and then driving the car back home. All right, okay, I think we will leave it there for today. You will have a quiz tomorrow, which I will post at some point today, probably near the end of the day. So make sure you check Google Classroom tonight for that quiz. It'll just be a PDF document that you can open anywhere on your phone, on your computer, whatever. Okay, give the questions on there a try. Yes.